Hello future engineers, welcome to my YouTube channel. Here is another lecture video in Algebra 8, particularly in advanced math about complex numbers, the trigonometric form, polar form, exponential form, so that we can evaluate other evaluations, operations with complex numbers, and of course, vectors. So first, let's have the trigonometric form of a complex number, and let's have the Argand diagram or a complex plane. So we have the real axis on the horizontal axis, the imaginary axis vertically, and each point, its complex point is denoted by a plus bi, where a is the distance of the point from the vertical axis, which is the imaginary axis, and that's the real part, a. And its distance from the real axis, which is parallel to the imaginary axis, is b, and its distance from the intersection, which is the origin here, is r, which is the absolute value or modulus, and the angle it makes with the real axis is denoted by theta. Same is true with the standard form in trigonometry, which is counterclockwise positive. And we call theta as the argument or amplitude. So r is absolute value or modulus, and it is from this right triangle square root of a squared plus b squared by Pythagoras theorem. Theta is called argument or amplitude, and r, the complex number, which is denoted by a plus bi, z equals a plus bi, is the Cartesian or rectangular form of a complex number. And a is the real part, b is the imaginary part. So where a from the figure is r, this is a, so r cosine theta, while b is from this right triangle, r times sine theta. And of course, tangent theta is opposite b over a. So z therefore is r cosine theta plus r sine theta. If you factor out r, then we'll have z equals r quantity cosine theta plus I sine theta. This is the trigonometric form of a complex number. And we have r equals square root of a squared plus b squared, the magnitude or the value, absolute value, and tangent theta is b over a. So same representation of theta, positive in counterclockwise direction. So if b is positive, then theta will lie, b is positive and a is positive, it lies in the first quadrant. B positive, a negative in the second quadrant, both negative in the third quadrant. And if a is positive, b is negative, it is in the fourth quadrant. So z is r quantity cosine theta plus I sine theta, which is abbreviated r cis theta. Cis means cosine I sine of theta. So z is r cis theta, then it is also r, then angle theta. This is called the polar form of a complex number. Trigonometric form, and this second part is the polar form. Then operations with complex numbers. Of course, if you have product, you can use your calculator, set it in the complex mode. But when it is not calculator aided, for example, then we use this, we transform complex numbers into trigonometric form so that we can easily operate them. So we have product, then it is also equal to the product of the absolute value or modulus, then the angles added. So z1, z2, quantity a plus bi times c plus di is modulus or absolute value of the first complex number times absolute value of the second complex number. Then their angles are added. Then the division, same principle, R1 over R2, then the angles are subtracted. So the modulus of the complex number in the denominator subtracted from the modulus of the complex number in the numerator. So we use this to have a complex number raised to any power, for example. So z to the n, it is equal to r to the n because it is r times r times r times n factors of r. Then angles theta plus theta plus theta plus theta, n factors of theta, so n theta. So that is, we have this Dumoivre's theorem, Dumoivre's theorem uh, that z to the n is quantity a plus bi raised to n, and that is r to the n angle n theta. So that's the shortcut, or in trigonometric form, r to the n, then cis n theta. So the angle is multiplied by n. Then we use this theorem in extracting the mth root of a complex number. So all you have to do, replace n by 1 over n. The modulus or the absolute value is the same except for the argument, which are separated 360 degrees over m apart, and m is the number of roots required. So that is, I just reiterate, to obtain the mth root of a complex number, replace n by 1 over m. There will be n solutions with the same modulus r except for the values of the argument theta, which are equally spaced at 360 degrees over m apart. So here the symbol m is the number of roots required. So we will demonstrate this in our example 3.1 or 4.1, I think. You should familiar with the exponential form of a complex number so that we can evaluate the logarithm or natural logarithm of a complex number. So the complex number may also be written after the Euler's equations. Let's have the Euler's equations first so that you can familiar with the exponential form of a complex number, and that is used in evaluating logarithms of a complex number. So z is r quantity cosine theta plus I sine theta, and from Euler's equations, this one is actually e to the I theta. So these are the Euler equations. One is e to the I theta is cosine theta plus I sine theta, and e to the negative I theta is cosine theta minus I sine theta. Therefore, this part here, you just replace it by e to the I theta, and therefore the exponential form of a complex number is r times e to the I theta. So that's it. That's the exponential form. Remember that this is product. So if we evaluate the logarithm of a complex number, then it is the logarithm of r e to the I theta, which can be broken down into logarithm of r plus logarithm of e to the I theta, which can be simplified into I theta times logarithm of e to any base, of course. So that's the exponential form. So theta in radians in this form, expressed in radians. So let's have this problem first. What are the square roots of quantity 3 plus 4i raised to, or square root of 3 plus 4i? So we must find the absolute value or the modulus, which is square root of a squared plus b squared. Then the angle, the argument, tangent theta is b over 3. And the square root is, remember, the absolute value is the same, while there are two roots, of course, expected because we have square roots here, while the amplitude or the arguments are separated equally at 360 degrees over m apart, where m is the number of roots required, which is in this case 2. So 360 degrees over 2 is 180 degrees. So R is 5. Tangent theta is 4 over 3 B over A. So theta is 53.13 degrees. And therefore, for the first root, this is the argument. For the second root, it is 360 degrees over 2, so 180 degrees plus this angle, 53.13 degrees. So we have z equals r cis theta. Square root of z, therefore, is square root of r, or r to the 1/2. Then cis 1/2 of theta. So square root of z is r to the 1/2. Then angle theta over 2, or 1/2 of theta. So square root of 3 plus 4i is square root of 5 cosine of 53.13 degrees over 2. Then plus I sine 53.13 degrees over 2. So using your calculator there, 53.13 degrees over 2, cosine of that is cosine of 26.565 degrees. And that is times square root of 5, that would be 2. And square root of 5 times I sine 53.13 degrees over 2 is 1. Then times I, so just I. So that's the first root, 2 plus 2i. For the second root, we have to add 180 degrees here, 360 degrees over 2, or 180 degrees. So still, square root of 5 times cosine 180 degrees plus 53.13 degrees over 2 plus I sine of the same angle, 180 degrees plus 53.13 degrees over 2. So using your calculator, it is negative 2 minus I. Therefore, the square root of 3 plus 4i, square roots of 3 plus 4i is equal to 2 plus I and negative 2 minus I. Then for the next problem, express 1 plus I to the 12 in the form of A plus BI. So we use the formula for Z to the N, and that is R to the N cis of N theta. So the angle is multiplied by N. So where R is square root of 1 square plus 1 square in this case. So we use this guide. Z to the N is R to the N cis of N theta. R is square root of 1 square plus 1 square, so that's square root of 2. And tangent theta is 1 over 1, both positive, so it is in the first quadrant, and that is theta 45 degrees. Therefore, n theta 12 times 45 degrees is equal to 540 degrees, which is a quadrantal angle, which is the negative x-axis. And cosine of 540 degrees, if you can remember without using the calculator, that's negative 1. While sine of 540 degrees is 0. So therefore, 1 plus I raised to 12 is equal to square root of 2 raised to 12 cosine of 540 degrees, which is n theta, plus I sine 540 degrees. Again, sine of 540 is 0, cosine 540 negative 1, and square root of 2 to the 12 is 64. That's 2 to the 6, or 64, times negative 1. So therefore, it is negative 64. It has no imaginary part, just the real part, negative 64. So 1 plus I to the 12 is negative 64. Now, because this problem is a problem that might be given in the board exams, and you are allowed to use a calculator, and your calculator has complex mode, so you have to set the calculator in the complex mode, and all you have to do is write this in natural display. But your calculator cannot evaluate of a complex number raised to 12 directly. The maximum power that your calculator can perform is up to 3. So knowing that it is only up to 3, then use that fact in order to write this into a form such that the resulting power of 1 plus I is raised to 12. So for instance, you write this as 1 plus I cube, then quantity square, so that would be 6, then quantity square again. So this is the first calculator technique. So you set your calculator in the complex mode and write it in this first case. 1 plus I raised to 3, quantity squared, then quantity squared. So that would be 1 plus I to the 3 times 2 times 2. That's 1 plus I raised to 12. Your calculator can easily process the result, and it is negative 64. You try that. The other one is, you may write this as 1 plus I cube, then quantity cube, that would be 9, then multiply it further by 1 plus I cube. That makes it 12. 1 plus I cube, then quantity cube, that's already 9, then quantity 1 plus I cube. So that makes it 1 plus I to the 9, then times 1 plus I to the third, and that would be 1 plus I to the 12. So we use this maximum power that your calculator is capable of. Beyond that, your calculator can no longer evaluate operations with complex numbers. So up to 3 only. And this will give us the same answer of negative 64, which verifies that the answers are the same. But if you're not calculator aided, then the angles are common, then we can still evaluate the n power of a complex number. But of course, this is for board exam preparation, so expect that you can use your calculator. Then let's proceed to problem 3 about evaluating logarithm of a complex number. So evaluate ln of quantity 12 plus 5i. So in this case, we have to express this in exponential form, which is z equals r times e to the I theta. R is square root of 12 square plus 5 square. So R is square root of 12 square plus 5 square, so that's 13. And tangent theta is b over a, so 5 over 12. So theta is inverse tangent of 5 over 12, and it will give us 22.62 degrees. Since we need to express this in radians, we multiply further by pi over 180 degrees, and expressing that in radians to 4 significant figures, theta is 0.3948 radian. Then the exponential form here, take ln of z is ln of r e to the I theta, which can be broken into ln of r plus ln of e to the I theta, and ln of e to the I theta is I theta ln of e, and ln of e is 1, therefore this is ln of r plus I theta. Substituting the value of r and theta 0.3948, so we have ln of square root of 13, or ln of 13 rather, plus I, then angle 0.3948 radians. ln of 13 in decimal is 2.565. So therefore, ln of quantity 12 plus 5i is 2.565 plus 0.3948 of I. Then this is the last problem. Perform the indicated operations and express the results in the form a plus bi and in cis theta form. So of course, you can use your calculator directly for this problem, but do not expect this will come out in the exam because of the easiness in operating this problem. So we have product 5 plus 12i, 4 plus 3i. So if you use your calculator, set it in the complex mode, then type quantity 5 plus 12 shift eng, close, then 4 plus 3 times shift eng, close. It will give us a direct answer. But before that, let's have expansion by algebra. 5 times 4 is 20, while 12i times 3i is 36i squared. Since I squared is negative 1, so that would be negative 36. So 20 minus 36 is negative 16. Then for the imaginary part, 15i and 48i is 15i, 48i, 63i. Therefore, this is negative 16 plus 63i. And in the second part, let's have the first part first. It is negative 16 plus 63i. For the second part, we multiply and divide by the conjugate of the denominator. The conjugate of the denominator would be quantity negative 24 minus 7i. Then divide the same thing, negative 24 minus 7i. Then perform the expansion and show that the answers are negative 297 over 625 plus 304 over 625i. Of course, if you use your calculator directly, quantity in the complex mode, of course, quantity 8 minus 15 shift n over negative 24 plus 7 shift n, your calculator will display this answer right away. But in algebraic way, not calculator aided, then you multiply and divide by the conjugate of the denominator. But here, let's transform this into trigonometric form or in polar form and show that these answers are the same. So for the first complex number, 5 plus 12i, the absolute value is 13. So 13 inverse tangent of 12 over 5. So inverse tangent of 12 over 5 is 67.38 degrees. I'm not showing it here because you can use that. You can use your calculator for the argument. Inverse tangent of 12 over 5 is 67.38 degrees. Then r is square root of 5 squared plus 12 squared, so 13. For the second complex numbers, r is square root of 4 squared plus 3 squared, that's 5. And the angle inverse tangent of 3 over 4, which is 36.87 degrees. So this is 5, is 36.87 degrees. Performing the product, so we have 13 times 5, 65. Then the angles added 67.38 degrees plus 36.87 degrees in cis form. So simplifying further, that's equal to 65 cis of 104.25 degrees, and particularly this is 65 quantity cosine of 104.25 degrees plus I sine 104.25 degrees. And using your calculator there, 65 times cosine 104.25 degrees, it should give us negative 16, while 65 I times sine 104.25 degrees, it should give us 63i. So therefore, that's negative 16 plus 63i. For the second part, as I said, or in cis form, 65 cis 104.25 degrees. You can set your calculator in the complex mode, then you'll have that right away as the answers. For the second part, just to use the trigonometric form of a complex number, r is square root of 8 squared plus negative 15 squared, so that would be 17. And the angle is inverse tangent of negative 15 over 8. Again, the angle is inverse tangent of negative 15 over 8. So this point lies in the fourth quadrant. And the angle, if you rely your calculator, inverse tangent of negative 15 over 8, your calculator will interpret it to be in the fourth quadrant. There are cases where the angle is in the second quadrant, but your calculator cannot detect that. It will give us an angle which is negative, so it should be measured in clockwise direction. And the angle, negative 65.928 degrees. It is in the fourth quadrant. Now, if you want to make it positive in the standard form, it should be measured in counterclockwise direction. So if it is in counterclockwise direction, that angle would be 360 degrees minus this 360 degrees plus negative 61.928 degrees. So that's also 17 cis 298.072 degrees if you use the standard form and positive angle. Again, to 98.072 degrees is 360 degrees, then plus this negative 61.928 degrees. Likewise, negative 24 plus 7i, this is in the second quadrant, but if you rely your calculator inverse tangent of 7 over negative 24, your calculator will display an angle in the fourth quadrant. So it's wrong. It should be in the second quadrant rather. That angle therefore is 180 degrees plus that negative value displayed in your calculator. So R for this complex number is 25. Square root of 24 squared plus 7 squared is 25. Then cis, the angle, as I said, is in your calculator. If you press inverse tangent of 7 over negative 24, it will give you a negative angle in clockwise direction. So it is interpreted in the fourth quadrant. But the actual position, terminal side of that angle is in the second quadrant. So in positive direction, counterclockwise, that angle would be 180 degrees plus the negative angle displayed in your calculator. That's why you'll get 163.740 degrees. And I think the negative value is 16.26 degrees. So that the positive equivalent is this. So again, the angle is negative 16.74 degrees in your calculator, inverse tangent of quantity 7 over negative 24, negative 16.26 degrees. Then in standard form, positive, that's 163.74 degrees. You may not change that if you want, but it is not the correct answer. It should be 163.74 degrees, or if you make that negative because it lies in the second quadrant, it is 163.74 degrees minus 360 degrees. So that's it, if you make it negative, but let's stick to that value. Therefore, dividing these two would be dividing the absolute value 17 over 25, then the angle in the denominator subtracted from the angle in the numerator. So that is negative 61.928 degrees. 17 over 25 is negative 61.928 degrees minus 163.74 degrees. And that becomes, you can also use the positive value if you want. Over 25 is 163.74 degrees. So that is 17 over 25 is negative 61.928 degrees minus 163.74 degrees. And that is 17 over 25 is of negative 225.668 degrees. That's the first. And the second one is 298, 17 over 25, then C is 298.072 degrees minus 163.74 degrees. If you want the other value, and the argument, or this argument here is 298.072 degrees minus 163.74 degrees. So that's 134.332 degrees. However, these two values will give us the same answers or values of the following. So that's the first. And using your calculator, it is in decimal form negative 0.4752 plus 0.4864i. If you use this, that's the same. Then actually this is equal to this negative 297 over 625 plus 304 over 625i. Then in cis form, 17 over 25 is negative 134.332 degrees, which is also equal to 17 over 25 cis of negative 225.668 degrees. So that's it for this video. I hope that you were able to follow the principles, equations, transformations, and the solutions to these problems.